All right. Good morning. So today, we're going to talk about what is both a basic device in itself, the amplifier, and it also serves as a real key example of both nonlinear analysis and small signal analysis. So today, dependent sources and amplifiers. So let me first spend a few seconds just pointing out to you some of the key points from our previous lectures. I also want to point out that each chapter in the course notes has a summary at the end of it. And if you take a quick scan of the summary at the end of each chapter, it highlights the major takeaway points from each chapter. It stresses what's important. And if you have to remember a few things, what are those things to remember? So to quickly review, we talked about a few primitive elements, resistors, voltage sources, and so on. And by now, you should have the facility to play around with these device elements. And then we talked about the node method. And this is kind of the workhorse of 6002, right? When in doubt, use the node method, okay? And this will work both for linear circuits and nonlinear circuits, okay? So if you see a problem or if you see a situation in real life that requires analysis, then as a first step, you should try to think of whether you can apply some of the key intuitive shortcut methods. Superposition, one of my favorites, the Thevenin method, Norton method, or the method that involves composition, that is very quickly analyzing circuits that have resistors in series and parallel. Okay? So if you can apply one of these quick intuitive shortcut methods, go do so. All right? If you can't, then usually you can resort to the node method, irrespective of whether the circuit is linear or nonlinear. So the last week was focused on the nonlinear method, or nonlinear circuits, and we spent the first lecture talking about a straightforward application of the node method, which gave us a bunch of nonlinear equations that we had to solve. In the last lecture, we talked about the small signal trick. What we said is, if you look at the whole space of nonlinear circuits, then within that space, if we focus on small variations, small perturbations about the operating point, then even the behavior of nonlinear circuits in that small regime would be linear. So small signal method And as an example, I showed you how I could take a highly nonlinear device like the garage door opener LED and using that build a pretty nice transmitter that would transmit music, and as long as they kept the signal small and operated the device in a region where its transfer curve was relatively smooth, and I biased or set the operating point appropriately, I would get a linear small signal response. Okay. So today, we're going to do a couple things. We're going to look at dependent sources. And the reading for this is section 2.6 of your course notes. and the dependent source will be a new element in your tool chest. We will also do amplifiers. And amplifiers are in section 7.1 and section 7.2 of your course notes. So before I begin with dependent sources, I'm just a huge believer in motivating things with real-world examples. Okay? So let me start by motivating why we need an amplifier. Okay, why we need to do things like this. Why do we even bother? And spend a few minutes really getting you to appreciate that amplification is fundamental. Okay, it's as foundational to life as high-fat potato chips and stuff like that. So let's do some basic examples here. So first, let me talk about why do we need to amplify signals? Why amplify? Okay, why do we care about building an amplifier? So an amplifier, think of a little box, and I apply some sort of small input, and I get a larger output. In this example, this may be a voltage with a swing of 10 millivolts, and in this case, the output might be another voltage with a swing of, say, 100 millivolts. And commonly, the amplifier, in addition to an input and an output, input port and an output port, may also contain a power port, okay? So that I can apply a power supply to the amplifier because commonly, as an amplifier signal, I'm looking for a power gain as well, an increase in the power provided by the output. So that's an abstract definition of a amplifier. And let's take a look at an example of why we may need this. So let's say I have a small, a useful signal, and let's say the signal has a 1 millivolt peak-to-peak, and I'm looking to transmit the signal over a wire to some other point. But let's say that in this environment, I get a bunch of noise that it's in a noisy environment, and in this environment, let's assume that some noise may get superimposed, and if I have a 1 millivolt signal and 10 millivolts of noise, then what I end up at the output is something that looks like this, and it's really hard to distinguish my 1 millivolt signal from that large amount of noise. On the other hand, if I did the following, if I took this signal and passed this signal to an amplifier, and I amplified the signal to be a much larger version of the same signal, let's say in this particular situation, 100 millivolt peak-to-peak signal. Okay, so I magnify the signal by a factor of 100. Okay, let's say it's a linear amplifier, and linearly amplify the signal to be 100 millivolts. Then in that case, if I added noise on top of this, it's going to be less discernible. The signal may look like this. Okay, my 10 millivolts noise would add on to it, but this is still pretty decent. I can still recognize the input. And so this is one application of amplification. If I need to send something from point A to point B in an analog, as an analog signal, then an amplified signal is less prone to noise attacks than a small signal. Not surprisingly, a large number of devices that are used in everyday life have amplifiers built into them. So, here's a little cell phone, and virtually every single cell phone contains an amplifier. So this is by the way, this is an all-digital cell phone. Okay? It's a Kyocera, I forget the number now. It's completely digital. Okay, but although they say it's completely digital, it turns out that a significant fraction of the circuitry is analog. In particular, so digital is sort of a marketing term to say that it's something special about this. But remember, there's a bunch of analog stuff. So Here's my little antenna from the cell phone. Okay, and typically the first thing that happens to a signal as it comes out of the antenna in your cell phone is, if you look at cell phone circuits or cell phone systems, will be something that looks like this. Okay, this and may have a label LNA. Okay, someone want to take a guess at what LNA might stand for? What's that? Linear amplifier. That's pretty good. So that's LNA. Close enough. A is correct. It's amplifier. What does L and N stand for? Low noise. Okay? So this stands for low noise amplifier. So, I get a really rinky-dinky small signal here, and then the low noise amplifier amplifies the signal. And in real cell phones, and for that matter, in your 802.11b or 802.11a or 802.11g wireless cards, same thing, antenna, low noise amplifier, and then you may have a bunch of processing. Okay? And commonly you have a bunch of analog processing, and then you convert the analog to a digital signal. Okay, I recall last week, I asked somebody in class here, how would we transmit the signal from point A to point B without being impacted way too much by noise? And he said, oh, go digital. Good point. Okay, so if I go digital, I can transmit the signal without noise being a real factor. But then the analog to digital converters need the signal strength to be a given value before it can chop it up into digital levels. Okay, so an amplifier is very fundamental. Okay, and so in this case, what may be a signal of a few tens of microvolts to be amplified to some large enough value that it can be further processed. So that's application of amplification in the analog domain. Let me talk about amplification in the digital domain. So that's in the analog domain. This amplification is in the domain where I have both analog and digital. Okay, and now let me talk about amplification in the digital domain. Okay, I'm going to argue that amplification is absolutely foundational to the digital domain. Okay, the digital abstraction would not occur if I did not have basic amplification. Okay, and in the next minute and 37 seconds, I will prove that to you. Okay, so let's do so. So let's suppose I have a very simple digital system. And the system simply contains a pair of inverters. So if I send a 1 here, it's a 0 here and a 1 here. It's a very simple, trivial digital system. And here's the input. Here's the output. And we said that for digital systems of this sort to work, they have to follow a static discipline. Okay, our signals and our circuits must follow a discipline for them all to work together. And the discipline we described comprised of signals adhering to certain voltage thresholds, so that all the components in the system could agree on what comprised a 0 and what comprised a 1. Okay? So the way we did that was we said that we would have a threshold called VIH, V input high, another threshold called VIL, V input low. Okay, and we said that this circuit must recognize signals that are higher than VIH, 3 volts, for example, as a 1. And simultaneously, any signal that has a voltage level less than VIL, say 2 volts, should be recognized as a 0. Okay, that was the input constraint. On the output, it had a similar set of constraints, where we had tougher constraints on devices, where we said that the output had to satisfy a output low constraint, output high constraint. What this said is that for this circuit to be called a good digital circuit that satisfied the static discipline, signals that were 1s here should be recognized as such, and if I were producing a 1 as an output, then the signal level should be higher than VOH. Similarly, if the signals are 0, then it should be less than VOL. So as an example, this may be 2 volts, this may be 3 volts, and this may be 4, and this may be 1. Okay, so input, I should recognize 2s and 2 volts and less as a 0. But at the output, I have to produce a very, very low value, 1. So I have some noise margin. So as an example, so if I were to plot the input and output, so I get my VIL here and VIH here. This is time. This would comprise a valid digital signal, 0, 1, 0, 1, and so on. Okay? Now, I had a tougher set of constraints at the output. I would have VOL, VOH. So at the output, okay, I'm required to stretch the 1s and 0s to a more, to be closer to be further apart from each other so that I get some noise margin. And the corresponding signal for our little circuit there would look like so. Right? If this is a valid input, then this would be the corresponding valid output. Okay? Need I say more? Okay, you can see that intuitively, look, there's amplification happening here, and the reason is that VOL is chosen to be less than VIL, and VOH is higher than VIH, so therefore a signal has to be stretched. Signal has to be amplified. Okay? And what's the minimum? What's the minimum amplification needed for the system to work? The minimum amplification is if I had a signal that looked like this. Okay, that barely skimmed the VIL, VIH level. Okay, so if signal were this high, peak to peak, VIH minus VIL, and what's the absolute minimum signal at the output? Would look something like this. Okay, barely skimming VOL and VOH. Okay, so the output, corresponding output level would be VOH minus VOL. Okay, so this is the absolute minimum amplification that my digital circuit has to provide. Okay, and notice VOH is larger than VIH. VOL is smaller than VIL. Therefore, this quantity needs to be greater than 1. Okay, so I've shown you both a simple graphical, intuitive explanation, and this is a slightly more formal proof that even the digital circuit really requires to have amplification built into it if it is to satisfy valid static disciplines. Yes? Yes. Is that the same? The question is that the same as gain? Good question. Yes. The term amplification has many, many variants. You could say gain. You could say amplification. You could say, increase in signal strength, and so on and so forth. Okay. And in fact, when talking about low noise amplifiers, people sometimes talk about having a low noise, high gain amplifier at the input stage. Okay. So let me pause there in terms of motivation. So I believe I've motivated every which way. Pure analog, analog digital, and digital. Okay, so I've covered every single base here. And so we need amplification. Okay, so let's look at how to build a fundamental primitive device called the amplifier. Before we do that, however, let me take a quick detour. It will be convenient for me, as I show you how to build an amplifier, to introduce a new device, a new element called the dependent source. Okay, let me introduce a new device for your arsenal of devices. Along with resistors, you've learned about a MOSFET, a switch, voltage source, current source, and now a dependent source. So dependent source looks like this. Okay, has an output port and has a control port. So dependent source, in its simplest form, has two ports, an input port and an output port. Remember, a port is a convenient pairing of terminals, okay, and I apply signals to such terminal pairs. But this is an abstract diagram for a dependent source. And to get a little bit more specific, let me show you an example of a dependent source. So let's say here's my input, and I label the terminal variables for the input. VC is the voltage applied to the input, and IC is the current into this terminal here. And here is the symbol for the dependent source. Much like a current source or a voltage source had a circle around it, the corresponding symbol for a dependent source is like so. So this example, for instance, is a dependent current source. I can apply the corresponding output variables, I0, okay? And I can say that the current I is some function. In this example, I've designed the example that the current through the current source, I, is some function of the input voltage or the control voltage VC. Okay, so notice that the current through a current source, the current through this current source, I, is some function of another variable. Okay, in this example, it's the voltage across its control port. Not surprisingly, this device is called a voltage-controlled current source. Or a VCCS. So, in like manner, I can also devise other forms of sources. So you can think of this as a device where a voltage controls an output current. You can think of all other combinations, current controlling current, voltage controlling voltage, current controlling voltage, and so on. So another example, I'll give you another dependent source. And in this situation, my output current is controlled by an input current, VC, IC rather, and I claim that I, for this one, is some function of a current IC. Okay, it's another dependent source where the output current through its output port is related to the current IC. And this is a current-controlled current source. Okay, it's a current-controlled current source. And if I had lots of time on my hands and I was looking to kill time, I'd sit around drawing for you other types of dependent sources. I would draw for you a current-controlled voltage source, and I could also draw for you a voltage-controlled voltage source. Okay, so that's an abstract diagram for such a source. And so let's do a few examples involving elements like this. To begin, just so you can build up your intuition, let me start by doing a simple, very simple circuit involving an independent current source. Okay, just so we can relate back to what we've been doing so far. So let's say I have some resistor, and I have a standard current source with current I0. This is an independent current source. Remember the circle? And some resistor R. And let's say I care about the voltage across the resistor. Okay, so I have current I0 flowing through it. So I can very quickly write down VR as simply I0 R. Okay, it's the drop across the resistor when a current I0 flows through it. Okay, so this is what you've been used to doing. Correspondingly, I can do an example with a dependent current source. And as an example, I'll use a voltage-controlled current source. Okay, voltage-controlled current source is a dependent current source whose output current depends on the input, on the voltage applied at the control port of the current source. So let me build a little circuit. Okay, so here's my current, and let's say this is VC, IC for the control port, and similarly, let's say my current I here is some function of the control port voltage, and let's say to be specific, it is some K over VC, some function. Okay, there are a variety of dependent sources that can be built, and here's a hypothetical device where the output current is related to the mathematically related to the input in the following manner. So let me build a circuit of the following form. So let's say I have a resistor R, and here's my circuit. Okay, and as before, let me look to figuring out what VR is. Now notice that I have to supply some voltage at the input so that the output can depend on the input. Because right now, I don't know what the input here. So what I'll do is let me apply VR over here. Okay, so let me make this connection. Okay, let me make the connection from here to here. What I've done is I've applied VR at the control port of the dependent current source. Okay, and I often draw a circuit like this. This looks pretty messy. I will often draw the circuit like so. R, VR. Okay, short form circuit drawing would look like this. This is a complete drawing where I show you the explicit connections to the control port. But oftentimes, when the control port does not have any other impact on the circuit, you can eliminate the, you don't explicitly show the control port, rather you can simply show the dependence of the output current on whatever circuit variable you have in mind. So you can draw a diamond like this and say its current is some function of VR, where VR in this case is K divided by VR. Okay? Okay, so let's go ahead and analyze this little circuit here and look at what this might give us. Our goal, as before, is to find out the value VR. So in this case, let's apply the node method to this node, and sum the currents into that node to be 0. Okay, so I'll sum the currents going into that node to be 0. The current going down is simply VR divided by R. Okay, and that is equal to the current that is going out of the node, and so that is equal to F of VR. And I know that F of VR is given by K divided by VR. Okay, a simple application of the node method. So then I collect VRs on the left-hand side, and I get VR squared is K divided by, K times R. Okay, and VR is simply square root of K R. There we go. I'm done. Okay, I've gone ahead and applied the node method to this. And when I have to figure out the current here, I simply reflect the fact that it depends on VR, like so, and I just go and solve the circuit. Remember, the workhorse of the circuit industry, the node method. When in doubt, apply it. Okay, it simply works. And notice this is a nonlinear circuit. Okay, the dependence is nonlinear, and I get the response like so. So, to plug in some numbers, supposing K was 10 to the minus 3 amperes per volt, and R was 1 kilo ohm, then I can plug the numbers in, and the kilo here cancels with the 10 minus 3, and I get VR equals 1 volt. Okay, this simply says if I build a circuit like this, then this voltage here will be 1 volt. So again, as long as you remember that the dependent source is simply another little circuit element, okay, and you usually draw just the output port for dependent sources and reflect the input and reflect the way that the control affects the current, that will suffice, and you get, through the application of the node method, the variable you're interested in. So let's do another example. Okay, of another fun current source, a voltage-controlled current source, and look at it this way. So let's say I have a resistor, and I have a current source, a resistor RL, and this goes to some, I apply a Vs here. Remember this short form notation, that's simply applying a supply Vs between that node and ground. Okay? And let us say the current ID through the device is some function of the current at its control port. Okay, so I'm not going to show you that. But remember that the device really looks like this, that there is a control port here. I'm not showing that to you. And let us say that I apply some voltage VI to the input port. The reason we often don't show the input port is for many practical dependent sources, the input has no other effect on the circuit. So for example, in this case, the input has infinite resistance looking in. So therefore, if I apply a VI here, it doesn't draw any current from VI. It simply, I simply applied the voltage VI. It doesn't affect the circuit in any other way, except in terms of how it controls the current ID. So let's say the current ID is some function of VI because VI is applied at the control port. Okay, and as I pointed out before, I oftentimes, just for clarity, just don't show this dependent source explicitly. Okay? So let's work the example. So as I said, I'm going to choose ID to be f of VI. And let's pick some specific parameters here. Let's say it's k by 2, VI minus 1 whole squared. Okay, and let's say this is true for VI less than or equal to 1 volt. And let us also say that ID equals 0 for VI less than 1 volt. Okay, but it's a dependent source, and it can have various forms of dependencies on the input. And I just picked an example of some hypothetical, or as yet hypothetical dependent source, the current through which is related to the input using a square law relation, VI minus 1 whole squared, as long as VI is greater than 1. And if VI is less than 1, then the current is simply 0. It shuts off. Okay? So I can go ahead and apply. So let's say I want to find out V0 versus VI. So I care about finding out V0, where V0 is the voltage of this node with respect to ground. Okay? So it's a slightly more complicated circuit than you saw up here, you saw up there. So let's go ahead and do this example. Start by applying the workhorse of the circuits business, the node method. And let's start with doing this for VI. Let's first do it for VI greater than 1. Notice the behavior of this is different for different ranges of VI. So let's first do it for VI greater than or equal to 1 and apply the node method. Node method says sum the currents going into this node, We know the voltage at this node, it's Vi. We know the voltage at this node, it's Vs. Okay, the only unknown is V0. And so let's go ahead and write the node equations for that node. So the current going up, let me simply equate the current going up to the current that has been supplied by this particular node here, and that should equate to, the two of them should sum to 0. The current going up plus the current coming down should sum to 0. So I get V0 minus Vs divided by R. That's the current going up. Plus the current going down must sum to 0. Plus ID must sum to 0. And ID is known to be K divided by 2 Vi minus 1 whole squared. That must equal 0. Straightforward application of node method. Current going up plus the current going down at this node should equal 0 because the total current leaving the node must be 0. Okay? So I can go ahead and simplify this, multiply throughout by, I call this RL here. So multiply throughout by RL and move all of this to the other side. So I get Vs divided by RL, multiply throughout by RL. I get Vs on this side. I take this term to the other side. This becomes a minus. RL multiplies here, so I get K RL that's the expression I get. V0 is given by Vs minus KRL divided by 2 times Vi minus 1 whole squared. Let me put a box around this because I will be referring to this more times in 6002 for a variety of reasons than probably any other equation on Earth. Okay, this is the first time you saw it. You saw it here. Okay? Mark it down. You will smile every other time we look at it in quizzes, and you will find out why this comes up very often in 6002. So I'll just give you in a few seconds to savor this big moment in your 6002 life. All right. Okay. So that's so it's pretty simple actually. I mean, this there's really not much. A lot of this stuff is just a plain old simple application of the node method, and things just fall out. It's just so simple. So the V0, I apply the node method, I get V0 for this nonlinear circuit. I can also do it for Vi less than 1. Okay, for Vi less than 1, when Vi is less than 1, what happens? ID is 0. Okay, since ID is 0, think of this as an open circuit. Okay, so there's no voltage drop across RL. And this voltage V0 is equal to Vs. So I like to see things in pictures. I'm not an equations kind of person. I'm much more of a graphical person. So let me draw a little graph to show how V0, to see the form of V0, and then let's study that little system a little bit more carefully. So this is page 7. I'm going to plot V0 versus Vi for you. And let's take a look at how this really simple circuit looks. This has got nothing. It's got a RL resistor connected to a supply and a dependent current source. I can apply some voltage Vi at the input. Very, very simple circuit. So let's see. So as long as Vi is less than 1, the output stays at Vs. Okay, that makes intuitive sense, right? As long as the current here is 0, this is like an open circuit here. If this is an open circuit, then effectively V0 is simply the voltage Vs. V0 simply appears here. Okay, if you want to grunge through KVL and KCL, go ahead. Vs minus RL times the current is V0, and the current is 0, so it's Vs. So this is simply Vs. When Vi goes above 1 volt, fun stuff begins to happen. Okay, when V0 goes above 1 volt, then this equation applies because Vi is greater than 1. This equation applies. And when Vi is a 1, 1 minus 1 is 0. This term cancels out, so this is Vs. Okay, phew. So I start off here. As Vi increases, what happens now? As Vi increases, this term here becomes increasingly negative, okay, and subtracting from Vs. Okay, so I get some behavior like this. V0 begins to drop. Okay, and it makes intuitive sense, right? As ID begins to increase, the voltage here will begin to drop because I'm drawing more and more current through RL. I'm dropping more and more across RL. So more and more drops across RL, so V0 begins to drop too. No big shakes here. So it looks something like this. I'll show you a little demo. But my claim is that you have just seen an amplifier. Whoa. You just saw an amplifier. So I snuck an amplifier by you. Okay? So okay, I just snuck an amplifier past you, and I'll show you why in a second. So let's take a look at this waveform here. Let's not worry about what happens way down here. We'll talk about that a little later. But look at this curve here. I claim there is amplification in the following sense. Focus on some change in the input voltage, delta Vi. Okay, and for that change in the input voltage, I get some change in the output voltage. Okay, for some change in the input voltage, delta Vi, I get some change in the output voltage. And guess what? In this, at least the way I have drawn it, delta V0 divided by delta Vi, if I can find regions of the curve where this is greater than 1, then I have amplification. Okay, so what's that saying? What that's saying is that if I apply some voltage here, okay, and I change that voltage by a small amount from, let's say, 2 volts to 2.1, okay, I'm going to find the output voltage. So let's say I go from 2 to 2.1 here. Okay, but abstractly out there, I might have an output that goes from 3 to, let's say, 2 volts perhaps. Okay, so for a 0.1 change here, I'm going to get a bigger drop here, say from 3 volts to 2 volts, giving me an amplification in this little circuit. Okay? So we'll see this again and again, and you'll really understand it. So I have a small change in the input, and I have a corresponding larger change in the output. So I've shown you an amplifier. I haven't shown you a linear amplifier. Okay, there's an extra charge for that. Okay, that will happen later. Okay, all I've shown you so far is an amplifier. And this happens to be a crummy amplifier. It's a non-linear amplifier because notice, this is not linear. I mean, it's a nice little curve. And so it's not linear. But, I promised you an amplifier and, I'm cheap and that's all you get for now. Okay, we'll see linear stuff later. But for now, I have a little amplifier. So let's do some real numbers and plot some numbers down and also look at a demo. So let's do an example. Let's say Vs is 10 volts. Let's say K is 2 milliamps per volt squared. And let's say RL is 5 kilo ohms. Okay? So let me substitute these values into that equation, and I get V0 is Vs is 10. So it's 10 minus KRL divided by 2. So K is 2 milliamps. 2 milliamps times 5 kilo ohms is 10. Divided by 2 gives me 5. And Vi minus 1 squared. That's what I have. So I just plugged in a bunch of numbers, and that's what I get. So what I'll do is let me just do a little table for you and plot using real numbers. Simply plot those values for you. So when Vi is 0, my current is 0, and I get, oh, that equation doesn't apply, by the way. That applies when Vi is greater than 1. Okay, so as long as Vi is less than 1, my output is simply Vs. My output is simply 10 volts. Okay, so all the way up to 1, my output V is, all the numbers are in, units are all volts. That's what I get. I come down to 2. If I plug in 2 for Vi, 2 minus 1 is a 1. So it's 1 squared. 5 times 1 squared is 5. And 10 minus 5 is 5. I get 5 out here. Okay? And then you can go and do the math. If it's 2.1, I get a 4 volts here. 2.2, I get a 2.8, and so on. Okay? Notice that the 0.1 volt change here resulted in a, when I go up a 0.1 change this way, it results in a minus 1 volt change there. So input went up by 0.1 volts. My output, kerplunked down by 1 whole volt. Okay, so a small change here resulted in a bigger change there, and that's the amplification that I am claiming here. Okay, so let me show you a little demo of a small device that I built involving such a dependent source. Okay. Let's do it here. Okay, so on my x-axis is Vi, and Vo is on my y-axis. And focus on this little point here. Okay? Right now, my Vi is 0. And so therefore, that's my output. I'm going to gradually increase Vi, and you're going to watch the output and see how it behaves. Pretty much like the little graph I drew for you. So I'm increasing Vi. Okay, notice that initially the current source is off, the dependent current source is off, so I move straight down. Okay, nothing happens until I hit a value at which the current source begins to come on, and then I begin to see a drop in the output as the current source begins to conduct current. Okay, you see that? So you see that as I increase the voltage Vi, boom, you see the huge drop. Okay, and notice that for a small change, I'm now getting a big drop in the output. Okay, so let's pause here for a second, and in the last couple of minutes, I want to cover one last point. Can you go to the continuous curve? Okay. Want to go up a little bit? Okay. So notice that the curve I've shown you up there looks like the curve up here. It goes and then kaboom, it kind of drops according to some kind of formulation that I've shown you here. Okay. In the last couple of minutes, let me discuss a small point. It's a practical issue. Okay? In the curve that I showed you, in the mathematics that I gave you, if we just go by the math, so what I'm going to show you now will distinguish a mathematician from an electrical engineer. Okay, a mathematician would have taken the curve and would have plotted it like this. This is 0. Okay? Mathematically, that equation says that starting here, this current simply goes down, kerplunk. But if I told you that this device that I have here, this dependent source, is a practical dependent source. It's a device that I have physically built, and I also say that it's a passive device. In other words, that it cannot produce power. Okay, it's like a little resistor. It doesn't produce power. It's a passive device. And so if it's a passive device, if I tell you that, then you're going to say, something doesn't make sense here. Mathematically, it says it should look like this. But what's special about a point down here? Point down here says that the output has gone negative. Okay, this is 0 here. Output has gone negative. Okay, and my current source is still supplying a current. Okay, so what, up here, the voltage across the device is positive, V0 is positive, and it's supplying a current, so it's consuming power. It's burning power like a resistor. Okay, like all bad little resistors do, they burn power. Okay, so here, on the other hand, my output has gone to be negative, but it's still sitting there sinking current. Okay, because VO is negative, but my current is still in the same direction, what has now happened is that the device has begun to supply power. So mathematically, this curve says that the device has begun to supply power. It turns out in our practical device, it's a passive device, so it cannot go here. Okay, so what happens is that somewhere along here, a model breaks down. Okay, the equation I've shown you for the current source, where is it? Here we go. This model breaks down. Okay, when V0 becomes very small, the model breaks down and it no longer behaves like a current source. Okay, it begins to behave more and more like a resistor, and what happens realistically is that the output goes down and then kind of becomes a zero hugging line. Okay, and I'll show you that in a second. And it doesn't, in this particular device, it doesn't really go down here. Okay? Let me just show you that part. So notice for that device, mathematically, just by that model, it should just have gone through the floor and punched through to the corridor below. But this is a practical device, and notice that the model breaks down, and that's what begins to happen. Okay, the device stops behaving like a dependent current source. Rather, it behaves like some corny old resistor or something like that and saturates out. Okay.